So we learned about power signals. Okay, like cosine of omega t, sine of omega t, e to the j omega t. All these are power signals. Okay, and they have finite instantaneous power, but when you Fourier transform them, you get delta functions. And delta functions do not converge. Like if you have j omega t, Fourier transform to something like, if this is omega naught t, for instance, it goes to 2 pi delta omega minus omega naught. Okay? And then if you apply Parseval's theorem, it says that the power in the time domain integrated is equal to 1 over 2 pi d omega f of omega squared. Then you find that the left-hand side does not converge, because if you substitute in here, then you essentially just have that. So the left-hand side is equal to that. And if you look at the left-hand side, substitute that in there, you get 1. When you integrate this 1 from minus infinity to infinity, you get infinity. So W tends to infinity for this power signal. Okay? And of course, the delta function itself has infinite energy. By the same token, you can prove that this thing Fourier transform to 1, and that the energy in the delta function is equal to 1 over 2 pi minus infinity d omega is equal to infinity. So delta function also has infinite energy for that reason. Okay, and we learned something very important in the last lecture, which is that the Fourier transform of an impulse train is an impulse train. And this is something very, very, very important for you to commit to memory. Okay, you have an impulse train on the left-hand side. If you Fourier transform this, you get an impulse train in the Fourier space. Okay. Are there any questions so far as to what we learned from the last lecture? Okay, if there are no questions, we're going to talk about sampling of analog signal and reconstruction. Okay, we're going to talk about section 9.3, which has something to do with sampling and analog signal reconstruction. What this identity gives you is something very interesting. That if I have an analog signal, say a voice signal that looks something like this, say, as a function of time. What this identity tells you is that I don't have to send this signal for all time. I need to only send its value at a certain sample interval. Okay. I only need to send the digital version of this signal, which schematically might look something like this. That f sub n might look something like this, like this, like this, like this, like this, and so on. Okay. If I need to only send a sampled version, which is called the digital version, this is analog. This is the digital version, which is the value of the analog signal at only certain prescribed location. I need a lot less memory to send a second signal. I can design more efficient systems to send a second signal. Okay. And secondly, I can send a second signal without error by converting, like this might be 9.36 in value, say. I can convert this 9.36 into binary signal. Okay, all computer scientists know how to do that. Convert a number into zeros and ones. And instead of sending that 9.36 over the airspace, I send 0 and 1. Okay? And there are error correction codes for sending digital signals. If there's an error in this digital signal they send over the internet or the airspace, you can do a reset so that there's almost no error in this kind of thing. You can also burn this kind of value into your CD-ROM, your VCD or your DVD. Okay, once they're burned into your DVD, they're burned in terms of zeros and ones. You almost get no error in the value of this number 9.36. Whereas if you record this with a tape recorder, this value might denature and deteriorate over time and becomes worse and worse. Okay, so let's see how we can do that. And let's prove that this can be done using this identity over here. Okay, so let's assume that I have a time signal f of t, which is the analog signal. Okay, now I'm going to multiply that time signal with this signal over here. I create a digital version of this signal, okay, which is equal to f of t times the impulse train. Okay, I know that I can bring my f of t inside. Okay, using the sampling property of the impulse function, or the shifting property of the impulse function, I can replace this f of t. Every time when t equals nt, I can replace it with what value should I replace it here? Yes? F of nt, yeah. Okay, you just can let t equal to f of nt. So this sum is the same as this sum. Okay, so this sum very much looks like this picture over here now. Okay, this sum very much looks like that picture over there now. I want to convince you that sending this over the airspace or a channel is the same as sending this over the channel, the same channel over the internet. And let's see how we can see that. Okay, so let's call this thing just f sub n, which is a digitized version of the original signal. Okay. So, if I have the digitized version of the original signal, I write it as equal to this f sub n times delta t minus nt. Okay, I'd like to know what the bandwidth of this signal is. So if I take the Fourier transform of this digitized signal, okay, it should be equal to this thing convolving with the Fourier transform of that thing. Okay, so it should be the same as the Fourier transform of the original signal convolving with the impulse train in the Fourier space. Does everybody agree that if I digitize this signal, which can be written as above, or can be written in its original form, the Fourier transform of this digitized signal is just this original spectrum convolving with the impulse train. Okay, let's assume that the original spectrum f of omega looks something like this. Okay, let's assume that it looks something like that, and let's also assume that way in the textbook. And so it has a bandwidth of B, so the signal vanishes outside this bandwidth. The original signal has a spectrum, something like that. It can draw other shapes, that's fine. Triangle is the easiest to draw, so I draw a triangle. Okay? So if you were to convolve this with that, it's quite easy to convolve a function with an impulse train. So what I need to do actually, to save some space, I draw this picture to be smaller, convolving with a picture of an impulse train. Okay, this is omega. And if I draw this picture of the impulse train, I will have impulses located as such. And this is 0, then first one is 2 pi over t, the second one is 4 pi over t, the third one is 6 pi over t, and it goes on and on. Okay, minus 2 pi over t, minus 4 pi over t, minus 6 pi over t. It goes on and on. Okay, now you can pictorially convolve these two functions. You can pictorially convolve them, and if you convolve a function with a delta function, what do you get? You say if you convolve with this function, which is located at the origin, if you convolve that with that, what do you get?
Bunch of little triangles.
The little triangle back, right? So let me, because I didn't have enough space in this thing, let's assume that my t is small enough so that this impulses are actually spaced quite far apart. So if I were to get the first result, I will have the first one that looks something like that. Okay, so 2 pi, this is 2 pi b, this is minus 2 pi b. And then let's assume that the next impulse over here is actually 2 pi over capital T somewhere here. Okay, and then there's another impulse over here, which is minus 2 pi over capital T. So if I convolve the function with this second impulse over here, what do I get over here? I get another triangle, right? Of the same shape. Okay? This is the triangle with the same shape, and then this is plus 2 pi b. You know what it is. This plus 2 pi b over here minus 2 pi b on this side. Okay? And this is the spectrum of f of d omega. It will look something like that. And I keep counting the other one. This one will give me a triangle peak about here. Okay, and you know where these locations are. This is plus 2 pi b over here minus 2 pi b over there. And these triangles keep repeating themselves. Okay, but each time centered at the location of where the impulses should be. So there should be a 1 at 4 pi over t, and then there should be 1, and then there should be minus 4 pi over t, and then another 1 over here. Okay? And what is the height of this triangle? What height should I give to this triangle?
Half of omega?
What is that?
Half of omega?
Yeah, let's assume that this is f0. Okay, what height should those be? The height of the original triangle when they convolve with this impulse train. which has a magnitude of 2 pi over capital T. So this should be f naught times 2 pi over T, right? All these heights will be the same. They should all have the same height. Okay? So what it means is that the digitized signal will have this kind of spectrum. And what do I do if I want to recover the original spectrum? I pass this to a low-pass filter. Okay, I pass this to a low-pass filter that picks out only one of the bands. Okay, this is also called a baseband. Okay, pick out the baseband of the signal. Okay, and then voila, I got the original signal back. Okay, did you see how it's done? How wonderful this recovery of the analog signal from the digital signal is done. Okay. So you see that it's very important that you pick T to be small enough. T to be small enough so that these triangles don't overlap. What happens if you pick T to be not small enough? T, this capital T represents the interval or the spacings. Okay, this is T, 2T, 3T. So this T actually represents the spacings of this impulse train. Okay, and when you multiply this by this impulse train, you're actually sampling the signal. If your capital T is not small enough, this signal will be poorly sampled. It might be sampled here, here, and here, and here. And unless you're a magician, you cannot recover the original signal if it's sampled like that, right? But if T is very small, then you get this signal sampled at all these locations. And it doesn't take a genius to figure out that if I do some work, perhaps I can recover the original signal. Okay? So you can see that for that diagram also. If T is not small enough, the triangle will start to overlap. Which means that T is called the sampling rate, or 2 pi over T is called the sampling rate. If the sampling rate is not high enough, you cannot recover the original signal. If you just have an analog signal, just sample at this 2 point. You need a magician to recover the original signal. Okay. So what happens if you don't sample at a high enough rate? T is not small enough, so your sampling rate is 2 pi over T. Okay, you will have the first triangle over here. Okay. And then if T is not large enough, then the second triangle might be standing over here and overlap with the first triangle. You will have a picture of something that looks like this. This is the case of low sampling rate. Okay? And if you do a low pass filter, what happens? Can you pick up the original baseband? You cannot, you get corrupted. Okay, you pick up signals that you do not want to have in the original baseband. This effect is called aliasing. Okay, so given the bandwidth of the signal to be such, how must you pick T so that there's no aliasing effect? Aliasing is bad. Okay, to get rid of aliasing, you need to have 2 pi over T larger than at least twice the spacing of this. This must, together with this, must be larger than 4 pi b. Okay, can you see from the picture that this inequality has to be satisfied? And if this is satisfied, it means no aliasing or no overlapping of the baseband with the sidebands. These are sometimes called the sidebands or the upper bands. Okay, so if this is satisfied, then you have the fact that you have the fact that 1 over T is larger than 2 B. Okay, you need this kind of sampling rate. If you think of 1 over T as the sampling rate or the F or the frequency of sampling, it must be twice the frequency. If this is the frequency, the highest most frequency you have in the original signal that you have. Yes?
In the overlapping area, should the F omega value add up together?
Yeah, they would, right? If you think of this picture. If you think of this picture, when you convolve this picture, you get one, and then you go and work on the other impulse, you get the other one in the overlap region. The original triangle will add up with the other triangles. So you get an erroneous answer over here, because you have the sum of the two pictures. And in textbook, you draw something like that, okay? You get that picture only if it's real value. Okay? If things are not real value, when things are complex value, then they may not add linearly together. Okay. So this is wonderful, right? You figure out how to transmit signal using less work. Yes, Mark.
On the first picture, or the top graph, why do you have it as 2 pi b? Is it because bandwidths are usually in hertz? And that,
why this is at 2 pi b?
Yeah, like why is it 2 pi on bandwidth?
Oh, bandwidth is usually described in terms of hertz rather than radian. Okay, so you say that bandwidth is 30 megahertz or 20 kilohertz or 40 gigahertz. So it's usually mentioned in terms of hertz. So that's why you multiply by 2 pi to get this omega. Okay, omega equals to 2 pi f. F is in hertz. Okay. So are there any questions so far regarding this?
So these impulse streams, when you convolute on the real life, it's still going to be the perfect shape because we can't make impulses perfect, right?
Well, you only have to make this one. You only have to do the first step. The other is theory. Okay, this step is what you have to do. You have to sample the function at that value, and then if you are able to sample the function, then you can construct this signal. And you don't actually send this impulse over, you send this signal over. Okay, of course you have to send them at a certain interval. You cannot send them at an infinite rate. So maybe you send them at a certain rate. You send them at a certain rate, but bandwidth is so high now that you can afford a lot of bandwidth. Okay, in sending this signal over. Now for a voice signal, B is about 20 kilohertz. Okay, for a voice signal. You don't get things above 20 kilohertz for a voice signal. And then you can have microwave systems that work at gigahertz. Gigahertz is 1 gigahertz is 10 to the 9 hertz. Okay, 1 kilohertz. 1 kilohertz is 10 to the 3 hertz. So if you use microwave channel to send your thing, you actually have a surplus bandwidth of 10 to the 6. Okay, that means that if your things are, say if you send a 10 kilohertz signal, which is most of the voice channel, you have 10 to the 4 hertz. So you still have a surplus bandwidth of 10 to the 5th, which is 100,000 times faster than your thing, which means that if you want to send this voice signal correctly, okay, you have to sample it at the rate which is twice the bandwidth of the voice signal. Say the voice signal is 10 kilohertz. That means you have to sample this at 20 kilohertz. Okay, that's what the sampling theorem tells you. So you have to sample this at twice the rate. Okay, So you have to do this twice as fast, but with the kind of technology that we have, we still have a lot of room in between these two signals, right? We can do a lot of action. When we send this signal gets sent so much later in the time scale of a gigahertz signal. So you can do a lot of things. And what do? You convert this signal into zeros and ones, okay? And send it as a digitized signal rather than as a number. And then you can put a lot of zeros and ones in this interval, given that you have so much surplus bandwidth. Because if you have a 10 to the 9 gigahertz, you can send a lot of zeros and ones. Okay? Is this understandable, or is this not understandable? So maybe it's good to gain some intuition as to what you actually do in the real world. So you sample this. Actually, you do not have to have the knowledge of this function precisely at this location. You have some fuzziness. You can actually think of it as a pulse of a certain width rather than a pulse of a zero width. Okay? Because if you have a true delta function, you actually have to have a pulse of zero width. And we don't have to bet that idealized in the real world. We can make these impulses fat and having a finite width. What does that do? What does that do? Okay? And actually, it does not change this theory very much, which means that actually does not change this theory very much. What it does is that instead of sending this signal, you might have a signal that looks something like this. Fn, let's call this Fn, with a pulse, which is not ideal delta function, but just a rectangular pulse. Okay, so you might have this kind of approximation in the real world when you send this kind of thing. And so one way to reconstruct this system is to have a system that looks something like this. Let me see if okay. So, so actually I'm missing a factor of 2 pi over here. If something multiplies in the time domain, it is equal to convolution in the frequency domain, but there should be a factor of 2 pi. Okay, I'm missing that factor of 2 pi over there. So that thing that I plotted just now should just have 1 over t rather than 2 pi over t, because the 2 pi cancels. So this triangle is over here. F of d of omega should just be 1 over t in height. And then they have repetition. Okay, they have repetition of that thing. And then, so if you want to design the low-pass filter, the low-pass filter should look something like this and re-equalize the amplitude. And the low-pass filter should have this amplitude of t multiplied by omega over 2 pi over t. Okay, and if this period here is pi over t. Okay, this is actually 2 pi over t. This is 0, and the low-pass filter can just pick up the baseband. And that is the design of the low-pass filter that would work. Okay, So a way of designing this system might look something like this, that you have a digitized signal that you have measured, okay, f of n, which is f of nt, okay, and then you multiply by some impulse train. The impulse train need not necessarily be idealized, okay, it might just consist of pulse function, and then what you have is that you create a time signal that is sum of the digitized signal times the impulse train. Okay, and then you have this going through a low-pass filter, which is a low-pass filter. Okay, and this low-pass filter will look something like that. And then out comes your signal, y of t. Okay, and it will look something like that. And your p of t might not be the ideal delta function, but it can be a simple rec function. Okay, it can be this function instead of the ideal delta function. In the limit, when epsilon goes to 0, you get back the delta function, but we don't have to construct an ideal function in real practice, so this impulse function would just look like this. And if you take the Fourier transform of this, it looks something like this, a sinc omega epsilon over 2. Okay? So if you have the Fourier transform of this, you get that, and how the sinc of this thing looks like when epsilon is very small. So if I were to plot this, okay, so when epsilon is very small, it actually goes as starting with 1 over epsilon, and then it goes to first zero crossing. Okay, where's the first zero crossing of this sinc function? When epsilon times omega over 2 equals to pi, right? So its first zero crossing, if I plot this as omega, its first zero crossing is omega equals to 2 pi over epsilon. So if epsilon is very small, the first zero crossing is actually very far out. So this will look like a very flat function, very, very flat. And epsilon goes to 0. Okay? So what you have then is that so what you have at this stage is that you can think of it that way. You can think of it that so you can think of it this way, that these are impulses. Okay, impulses can only be reconstructed with very high frequency content. Okay, so when you have this impulse train, because it needs a lot of high frequency content, you need a lot of high frequency components in the Fourier space to reconstruct this impulse train. Okay, so what happens then is that if you were to distort the shape of this impulse train and approximate with something that is not that singular, you will only change the Fourier component of things that are out there. Okay, you will not change the low frequency component that much. So what happens is that the choice of this thing will not affect the baseband, but only the upper and high frequency bands. Okay, yes?
So that drawing you have up there, should the input to the entire thing just be S, and then once you multiply it by the sum of the pulses, then it changes to S of n?
What is that?
So like where you have S of n on the top left, shouldn't that just be F?
I can actually just put an f of t here if you want to think of it that way. Okay, but actually when the signal comes in, I'm actually measuring this thing. Okay, I'm actually picking out these numbers. These numbers are sent to me.
But isn't that what comes out from multiplying it by the thing at the bottom?
Now this is actually recorded, say, in your CD-ROM. Okay, what is stored in the CD-ROM are sequence of these numbers. Say if the laser light reads the numbers, it will spit out this number in a sequence to you. Okay, and you want to reconstruct this signal from this sequence. So you have to have a way of multiplying this by a pulse. There will be some device. It's not as simple as this. Okay, this is kind of a simplified picture. But this device, take this digital signal you have from your CD-ROM, read by the laser light, and attach a waveform to each of the poles. Okay, so it's not this simple multiplication as in say in the textbook. Okay, when you do this, then you get this one is just a whole bunch of numbers that you read off, and then this one you will get a bunch of pulses.
So the